Recording is rolling. It's Thursday, August 25th. Yesterday, you guys were rolling Hot Wheels cars down an incline and you were getting lots of data. Now, there were different sets of data you're getting based on the group that you were in. So you could have been in any of these four groups. Okay. And we did have a spare about 5 minutes at the end of class, which would have been a good opportunity. You guys could have made these graphs. Well, one of these graphs, depending on which graph group you're in. Each of these corresponds exactly with one of these tables. For example, B versus D in the bottom left, B versus T bottom left. So you probably have one graph done already. Now, what we're going to do is I'm going to open the Excel page. I'm going to have you guys volunteer your data, and we're going to make 6 graphs. Those 4 I just flashed up there, plus an additional 2. And from that, we're going to figure out what's the relationships among these kinematic variables. So we've got time, tick, 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 and seconds. There could be displacement, how far something's going. There could be velocity, like how fast it's going. There's also acceleration. And I'm going to define this later and then derive some equations for you guys. Acceleration is a rate change of velocity, like the rate that you're speeding up or slowing down. Okay? We're going to derive these 3 equations starting from your lab data. All right, so that's the adventure we are about to be going on. Let's see, share screen 2. Slide over. This one's you guys right here. Okay, open up. What? Hold on, what's this about? Okay, I think we're good here. Ignore the data that's already there. Let me clear this out. Okay, what do you mean? All right, just give me enable editing. All right. All right, how about now? That should work. Come on. Yeah. Okay, get rid of this. All right, you guys don't see any of this. None of this counts. That's just made up numbers. All right, and here we go. Who was in a group who was changing out the mass of the car every trial? Who was taking lab weights to the car? Somebody was. All right, go ahead, Macy. What were your mass values?
0.58.
All right.
And then 52.81. 132.69.
132 points. Okay.
And then 66.7.
Okay, so yeah, those 4.
Yeah, but we had 2 other ones.
Oh yeah, keep going, keep going.
72.10. And then 122.35.
All right, so those are all masses in grams. Okay, now what were the corresponding times?
You had 3.39 for the first one, and then 3.28, 3.49, 3.34, 3.39, and then 3.29.
And that is exactly what that graph should look like. All right, good job with that stopwatch. And so if you were in that group, you probably have that graph already. Everybody else, just to save a little bit of time, because I got just enough time in class to do all the stuff we want to do this. Copy that graph, but I just care about the main elements. So the vertical axis, label that mass in grams. The horizontal axis, label that time in seconds. So you can get that from the title. See where it says mass versus time? Okay. So one rule for graphs is the title gives away what's on each axis. It's always the vertical axis versus the horizontal axis. So mass in grams, time in seconds. If you have time to go ahead and plot down to like 1 second, 2 second, 3 second, right, put the dots about where they go, and then shoot, and then line of best fit, or maybe it might be some kind of curvy line. So in general, I could call it a curve of best fit, which in this case is just a vertical line. Like obviously, that's just a vertical line. You guys see that, right? All right. So talk about graphs a little bit while you guys are jotting that down. All right, so one rule I told you already, that the title gives it away. It's always vertical versus horizontal, so mass versus time. Okay. How about this? If you have an independent variable and a dependent variable, there is a rule for what goes on which axis. What usually goes on your horizontal axis? Independent or dependent? You're independent, yeah, independent variable. Right? Which you might look at this and say, hold on a minute, isn't that like backwards? Because I thought we were changing out the mass and seeing how time responds, which is true. Because there's another rule that overrides that rule that says if time is ever involved, then as a rule, you always put time down on the horizontal axis, which is what's going on here. And do you guys see how it doesn't matter what the mass of the car is? it's the same time regardless. It's a little over 3 seconds to go that particular distance, right? So control for the ramp angle, control for the distance in this particular setup. Right, there you go. In fact, you know what that proves right there? That you proved what Galileo proved back in 1589. If you go back, say about 1,000 years ago, people assumed that heavier stuff would fall faster than lighter stuff because modern science did not exist, but people had logic. And Aristotle said, "Oh well, heavier stuff should fall faster than lighter stuff because logically, because there's a greater gravity force on it." Now, is there a greater gravity force on heavier stuff compared to light stuff? Yes, but that's not the whole picture. That's not the entire story. Heavier stuff also has greater mass, which means greater inertia, and the two effects cancel each other out. So Galileo said, "Hey, I'm not going to just do this armchair logic where I just like sit down in an armchair and think really hard about how the world should work logically. I'm going to do science, which was like this was like the birth of modern science. It's the same experiment right there. Ran to the top of the Leaning Tower, dropped lots of different stuff, different sizes off, right, and it all fell together, all hit the ground at the same time. Right, so everything fell at the same rate, regardless of how massive it was. Right, so you guys have that one. Okay. All right. So you guys know that the kinematic equations then are not going to involve mass. Mass has nothing to do with the motion of the car at the end of the day. Okay. Next group. Ooh, who is changing out the distance and measuring the time as a result? Who was doing distance versus time? Go ahead, Braylon. What were your values? Just the averages. What were your average distances? Well, just the distances, I guess.
10 centimeters,
10.
30 centimeters, 50, 70, and 90.
Alright.
And then we have 0.24 seconds, 0.40 seconds, 0.52 seconds, 0.72 seconds, and 0.93 seconds.
Okay. That's pretty good. I think that'll work for us. Okay, so X versus T looks about like that, right? Now, obviously, if the car is rolling a further distance, it's going to take more time, right? That's why the graph kind of increases. But I guess what we're trying to nail down more specifically is what exactly is that relationship? For example, if you double the distance, does the rolling time also double, or does it more than double, or does it less than double, right? So I think we can get it from here. Now, at a glance, that might look linear, right? You guys think that looks kind of linear, except that it actually isn't. And I'll tell you guys one hint how you can figure out that actually is not linear, even though at a glance it looks like it might be. Which is if you extrapolate back, you guys see how there's a pretty good sized negative y-intercept here, okay? And then what would that mean physically? Well, since the horizontal axis represents time in seconds, and the vertical axis represents displacement in centimeters in this case. What that would mean, that huge negative y-intercept, assuming this is a straight line, is that at time 0, the car would have a negative displacement. That's kind of like you let the car go and it immediately jumps backward up the ramp, which is definitely not what happened. Okay. In fact, I'm going to throw a 6 point on here. There's sort of an implied point, which is that at position 0, time 0, they should line up, right? If the car's had 0 seconds to roll, it should roll 0 centimeters. So I'm going to put that on here. Right. And now, okay, now it didn't look exactly so linear anymore, right? Right. Now, using that as a ground point, it looks like for the first second, first 0.2 seconds, I should say, the car rolls about 10 centimeters. And then the next interval of time, it's like 3 or 4 times as far. Huh. It looks like this is, here's ideally, this would actually take the shape of a parabola. This is close enough, right? So let's assume that's basically a parabola shape. So X versus T is going to be a parabola. Okay? You guys gonna get that? All right. So if you're doing this, you probably have X in centimeters for your vertical, time in seconds for your horizontal, put the points about where they go, and then draw a parabola. Okay? You guys got a parabola there? Okay. Now, you guys have seen a parabolic relationship even the very first week of the school. You guys remember I had you graph properties of circles? One of the graphs you guys made 3 graphs. One of the graphs was area versus radius. Remember that was a parabolic relationship, which looks a lot like what you're seeing on the screen right there. Because there's an equation, area equals pi r squared, right? So area compared to the radius, that was a parabolic relationship, okay? And then I had you make a manipulated axis graph. I had you graph area versus radius squared. Not radius, but radius squared. You guys remember that? And then remember that lined up in a straight line and the slope was equal to pi. So you still have area is pi r squared. Let's do a similar thing. Suppose you suspect a parabolic relationship versus any other kind of curvy relationship. We're going to manipulate this by doing x versus t squared, and hopefully that one will actually line up in a straight line. Right? You guys ready to see that? Right. Third graph. Here we go. Third graph. So same experiment, but we're going to manipulate this. Okay. Now that one ideally should have come out to a straight line relationship. Let's assume that it does, just to have the science story down here. I right click on one of these points, add trend line. I'm going to go to display equation on chart just so I can get lots of extra goodies and tell you guys about that. All right, so this is the third graph you guys are doing. Sorry about that. Let's go over here. All right, so displacement versus time squared, right? X versus t squared. So the vertical axis is still displacement in centimeters, but the horizontal axis is now time squared, which is what unit? It's not seconds, it's square seconds. Right? Second squared is the unit on the horizontal axis, right? Which is kind of an abstract concept, but then again, so were those circle graphs back in the day, right? Right, so we got an equation here. Let me blow up this equation so we can take a look at that, and let's interpret this while you guys are jotting down the rest of that graph. All right, so do you guys see how that line goes really close to the origin? You guys see that? In fact, ideally it would go through the origin, right? Because if 0 times passed, the car shouldn't have rolled anywhere, right? So Excel gave us an equation that's in the form y equals mx plus b. You guys see that? Right. But that plus b, that plus 7, isn't that really just like the error of missing the origin? But it should really just be plus 0, shouldn't it? Like plus 0, right? So we're going to throw out the plus 7, say, you know, graphically, you can see visually, just barely misses the origin. You should go through the origin, right? We're going to focus on the rest of that, the y equals 107x part. Right? Now, y is actually displacement. We're calling x. And where Excel gave us x, that's actually t squared, isn't it? So doesn't this equation say x equals 107 t squared? Right, you guys get that? Right. Now, one more thing. That 107 has units attached to it. All numbers in physics have units attached to them. Right? Well, except for a couple weird exceptions later. So how do you go from time squared and translate that into centimeters? That's to say, what's the slope of this line? I mean, the number slope of this line is 107. But that's 107 what? Well, rise over run. Doesn't it rise some number of centimeters? And the run is some number of square seconds? So if you do rise over run, isn't that centimeters per square second? Centimeters per second squared? Right? So this equation reads x equals 107 centimeters per second squared times time squared. Okay? Now, you can go to that incline at a 5-degree angle. You can drop a car. You can let it roll for some number of seconds. And you can predict, you can know how far it would have rolled. Just take the time in seconds, square that, multiply by 107 centimeters per second squared, and that will tell you how many centimeters that car has rolled. Right? Okay. You guys good with that? You guys got that third graph? All right. Moving on. All right, so we got 2 more experiments to go that were really similar in setup. I had you guys, okay, so now we're breaking up the speed gates. You guys remember those speed sensors, right? Now, some of you guys had measure how much time did the car roll for. That's one we're about to do. And some of you guys had measure like what was the distance the car rolled, right? So we're about to do V versus T. Now, this is a really important graph. You're going to see this all over the place in this class, right? Who did V versus T? Who did V versus T? Was measuring different times and speed. Yeah, Lily, what were your different let's go speed values. What were your speed values?
Okay, so for the first one we have 2.28 seconds,
All right. So time is 2.28 seconds.
then 2.66, 2.08, 1.53, and then 1.16,
All right. What were the corresponding speeds?
1.52,
Oh, let me do it. Let me expand some digits here. All right.
1.43, 1.24, 1.01, and then 0.71.
All right. Yeah, I think that will work. Right. So the more time the car's been rolling, the faster it's going. Show of hands. How many guys think that is a linear relationship? linear relationship. Yeah, turns out that it is. Right? And the linear relationship, or also called direct relationship, what that means is if the car has been rolling for twice the time, it should also pick up to twice the speed. Right? So V versus T. So you guys got velocity on the vertical axis, that's in meters per second, because that's what the speed gates are reading, and this meters per second. And the horizontal axis is time in seconds, right? And those really well line up into a straight line. If you like, I can also type in the implied point, which is that at 0 seconds, how fast was the car moving in 0 seconds? 0 meters per second, right? Because right? So it's sort of an implied point there. Let me do what I did before. I'm going to right click, add trend line, go down, display equation on chart, and okay, there's our equation. Let me bring us over here, blow that up. All right. You guys see, just like before, there's a tiny y-intercept, but that's basically 0, right? So we care about this part of the equation, right? And we're going to interpret this as the speed it picks up to v is equal to 0.58 times t. Now, 0.58 also has units. So that 0.58 represents the slope of this line, rise over run. Doesn't it rise some meters per second? And the run is seconds. Isn't that true? Right. So put it all together. Guys, what is meters per second divided by seconds? Is that meters per second squared? Right. That is the unit on the 0.58. So this says V equals 0.58 meters per second squared times T. Okay. Right. And in fact, the slope of this line has a special name in physics, starts with an A. What is the rate change of velocity called? Acceleration. So the acceleration of that toy car yesterday was 0.58 meters per second squared. Right? 0.58 meters per second squared, going down a 5-degree incline. Okay, so you guys graphed V versus T. This point's pretty well lined up in a straight line. Zip. V equals 0.58 meters per second squared times T. Okay. Now, like you could set up that incline 5 degrees. You could know if you know how long the car's been rolling for, like how many seconds, just multiply by 0.58, and now you know you could predict how fast that car is rolling. All right, you guys ready for the last experiment? All right, here we go. Last experiment was actually really similar to that setup, but I had you guys measure like how far did the car roll instead. Now, just like I said, V versus T, you'll see all over the place in this class. V versus X is a really rare graph to come up. You'll almost never see this, but there's a relationship. It's kind of fun. So let's do it. So who had this last experiment? V versus X. Who was changing out the distance and measuring that? All right, I'm gonna take a quick trip around the room and see if I see any lab papers. V versus X. Oh, actually, I think this is it here, right? Yeah. All right, yeah. All right, that's supposed to work. So we got, let's see, 10 centimeters, 20, 50, 70, and 90. And the corresponding speeds were these numbers. All right, that will work. Yeah, thank you. And so graph V versus X. So got velocity. Oh, get another digit here. So velocity on the vertical axis, that's in meters per second. You got displacement on the horizontal axis, that's in centimeters in this case. You know, we're mixing and matching units a little bit. That's okay. I really just care about the graph shapes, like the relationships between the variables. So the numbers are. And then, no, is that going to be a linear relationship? Let me throw in an implied point, maybe like 0, 0. Like if the car hasn't rolled anywhere, hasn't picked up any speed yet. It's kind of true too. Okay. Does this look like it kind of hooks down? Like it definitely increases, like more rolling distances, it goes faster and faster. Do you guys see kind of like diminishing returns, right? Like it it's really steep in the beginning and then it kind of curves off, kind of hooks down. You guys think that might look kind of like a square root curve? You guys know what a square root curve, right? It's like a sideways parabola, right? I think that's what that is. Right? Now, suppose you suspect that, like, I think that might be a square root curve, versus any other kind of diminishing return. It's like, how do you know it's not a cube root or something else? Right? So we're going to do one last graph, which is going to involve axis manipulation. Now, this one, I'm going to square the v, like square the speed. Tell you what's coming up in this last graph. Right? And so it's going to be v squared versus x. Okay. So v versus x, you guys see like that hook, like a square root hook, like a sideways parabola. Okay. You guys got that one drawn? So v versus x, whoosh, sweep out square root. Right. Now this last one, just take the same data. Kind of did this with the last one. I think I forgot to point this out, but just squared all the speeds in this case. Let's bring out another decimal point. Okay. See how I just copy pasted the data 10, 10, 20, 20 for x, and then speeds, just square those. Right. Right. And that should work out to a straight line. Ooh, pretty good, pretty good. So I'm going to right click on one of these, add trend line. Show me the equation. All right, get an equation like this. That y-intercept is pretty much 0. Let's blow this up. Aha, there you go. Okay. So that's the square of the speed in meters squared per second squared is 0.0087 times some weird unit times the distance that the car rolled in centimeters. We are kind of mixing and matching meters and centimeters, but that's all right. Huh, interesting. And the purpose of that graph is just to show that the previous graph is in fact a square root graph, because this one does line up in a straight line. Right. So you guys are going on your last graph. Vertical axis is speed squared. Horizontal axis is displacement. And then all the points line up. Direct relationship. So you do have to keep a pretty good pace today to get the stuff in 48 minutes here. I'm recording this, I'm going to put it on Google Classroom. If you need to see this one more time, then this will be on Google Classroom tonight. Let me switch over. Oh, there you go. Okay. And let's put this all together, because where we're going with this is we're headed towards these 3 kinematic equations. These 3 kinematic equations describe all kinematic motion, as long as there's constant acceleration. Okay. Now, if you're keeping track, there's only 5 variables that are on this list. There, or anywhere in these equations. There's t time in seconds, which you're measuring yesterday. There's x displacement, which you could do in like meters, for example. Okay. I see a couple of v's. What is v naught? Initial velocity, right? And then vf is like final velocity. Now, as those cars were going down those ramps yesterday, they were going faster and faster and faster between point A and point B, where there's like a bajillion different velocities. But see how with these equations, you really only care about 2 velocities, the first one and last one. So beginning of the interval, end of the interval. So we got time, displacement, initial velocity, final velocity. And there's only one other character on here, which is what? What does the A, and what does the A stand for? Acceleration. And acceleration is a rate change of velocity. Okay. Now, those are the only 5 variables anywhere on that page. Okay. Now, those are all spelled out on the page that I gave you guys the very first day of school. You guys remember this packet? Got variables, what it stands for, the unit, a little bit of notes and some equations. You guys remember that? So just point out that that is there. Okay. Because I'm going to take your guys' graphs and some basic definitions, put everything together, and we're going to derive these. Okay. So here we go. Let me back way up and start with something that is non-accelerating that you could have known before you ever walked into a physics class, which is, suppose you're driving up I-95 cruise control, just constant velocity. So could you guys see this? How far you go is just how fast you're going times however much time you're driving. For example, suppose you are going 60 miles an hour and you do that for 3 hours. 60 miles an hour for 3 hours. How far have you gone? 180 miles, right? Or suppose you see a sign on the side of the road that says 180 miles away, it's the next town, right? And you're going 60 miles an hour. Could you in your head say, going 180 miles at 60 miles an hour, it's gonna take me 3 hours to get there? You guys could do that, right? Or you might say a different version of this. Could you rearrange this algebraically, get velocity is displacement over time? These two say the same thing, right? Just rearrange a little bit. Okay, now this is all constant velocity, which is the same thing as saying no acceleration, or acceleration equals 0 meters per second squared. In fact, if there's ever non-accelerating, just constant velocity, that's the only equation you care about. There's two different versions of the same equation. That's all you care about. Okay. But what if you are accelerating? Well, let me write down the definition of acceleration. Acceleration is the rate change of velocity. I can write that in equation form. A for acceleration is a variable equals rate change of velocity. So like final velocity minus initial velocity, all divided by the time interval that it happens in. Okay. And an acceleration, see, it's something that you can feel. So we draw you guys a little picture over here. Explain some. I'm about to rearrange that equation, but not for a couple minutes here. Okay. Suppose you are in a car and you're looking at the speedometer. Okay, here's the speedometer. It says so many miles per hour, but in this class we're going to use meters per second. Very similar idea. And the needle's pointing at like some speed that the car's going. Just cruise control, right? You're just up I-95. Okay. Now, if you are a passenger in that car, let's say your friend's driving the car, you're a passenger and you're blindfolded. Can you feel how fast the car is going? Yes or no? No. You can't tell if the car is going 50 or 60 or 70 miles an hour. You can't feel that. Hey, are we on a giant spinning planet right now, moving almost 1,000 miles an hour? Yeah. Can you feel that? No. All velocities are relative. You cannot feel velocities, but you can feel something in a car. What can you feel in a car? Accelerations. Okay. So as a driver, there's three things that the driver can do that you can definitely feel. What's one thing the driver can do? The brake, right? What's another thing the driver can do? Like slam the gas pedal, right? I bet you feel that, right? Slams the gas pedal, the needle moves. Slam the brake. You guys can feel that, right? You feel like throwing backwards and forward. Right? You guys feel that? There is a third control that the driver can do. It's a little trickier to think about. What else can the driver do? Steering wheel, right? Steering wheel. Okay. Now we're going to save the steering wheel for a few weeks from now. So just for today and like the next couple of weeks, we're interested in just forwards and backwards. But hold on to that idea because that'll come back in the future. Right? Now, here's the rate change of velocity. So the rate this needle moves. Can you guys imagine if the driver like taps on the gas a little bit, this needle slowly moves. You might feel it a little bit, push back into your seat. But if he slams on the gas pedal, like, wow, man, you really feel that. So you can definitely feel the magnitude of acceleration. If he slams brakes, so the rate change of velocity, acceleration, you can definitely feel that. What I'm going to do is apply a couple of algebra steps and just rearrange this equation and solve for the velocity that you arrive at based on these other variables. Okay. Cross multiply the t. A times t is the change in velocity. Then I'm going to take the initial velocity, add it over, and also switch both sides while I'm at it. You get final velocity is equal to initial velocity plus acceleration times time. Okay. Now, these three lines, boom, 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 all say the same thing. They're just rearranged a little bit. So why did I do that? I did that because that boxed in version at the bottom is exactly this formula right here. It's it. The velocity you build up to is the velocity you started at plus acceleration times time. And if you start from rest, it looks even simpler. If you start from rest, initial velocity would be 0, right? It's just what's the rate you're speeding up times how long do you do that for? That's the speed you pick up to. Okay, you guys get that? Okay, so that's definitely the first one I wanted to do for you guys. Okay. Now, what about these other ones? Okay, so the next one we're going to do is this top one. And actually, we kind of have part of this already because remember I told you guys for constant velocity, if there's no acceleration, it's just distance equals speed times time. That looks like that, doesn't it? X equals vt. As long as you're just constant velocity, that's true. Okay. What about this other part? What is the whole like 1/2 at squared? Okay. Now this one's gonna take a little bit of explaining, but we will get there piece by piece. Okay. So it's gonna be a lot on this page. Do a picture, a table, and 3 graphs. Okay, and put it all on one page because I want you to see this all side by side. If in your notes, if you want to put this on like 2 different pages or something, that would make sense. But so this guy's going to the edge of a cliff and he's gonna drop the ball. And let's say I'm taking a picture every second. So after 1 second, maybe the ball's here, and then 2 seconds, 3 seconds, 4 seconds, and then 5 seconds, this ball is about to crash land at the bottom of this cliff. Right? Is that? Right. Hey, do you guys see how it's like spreading out? Right. That's like displacement versus time, but that's kind of the trickiest one to figure out, but we're gonna get there. We're gonna make a 4-column table. But we're gonna say how much time has passed in seconds, acceleration in meters per second squared, what's the velocity in meters per second, and finally displacement, how far has the ball fallen in meters? Right? Oh, well, I told you the times already, so we're gonna go 0 seconds, 1 second, 2 seconds, 3 seconds, 4 seconds, and 5 seconds. Tick, tick, tick. Do you guys see how this scenario? I don't know. I'm talking about a guy dropping a ball off a cliff. See, that's going to be really similar to what you did yesterday with the car rolling down the incline. See, it's being pulled under its own weight. It's speeding up. In fact, the lab you guys did yesterday is the scenario, but just slowed way down. So this is very similar to what you did yesterday. Okay, just at 5-degree incline. Okay, so I'm going to set up 3 graphs with you guys. So let's do graph, graph, graph. And set up 3 graphs. We're going to go how far is the ball fallen in meters as a function of time in seconds. We're going to go how fast is the ball picked up to in meters per second as a function of time in seconds. And also the acceleration of the ball, meters per second squared, as a function of time and seconds. Notice every one of those axes I have labeled variable unit. Okay? Variable unit, variable unit. Variable unit. You guys got that in your notes? All good? All right, let's go start filling out this table. See if we can make sense of this, put this all together. So if this guy drops the ball is starting from rest, just like your guys' Hot Wheels car started from rest yesterday. I'm gonna start, let's go to this column right here. How fast is the ball moving right as you're releasing it? 0 meters per second. Okay. Now after 1 second, how fast is the ball picked up to? Would this number that goes right here be different for different planets? If you go to Mars or go to the moon, is the ball going to pick up to different speed after falling for 1 second? Yeah, right. So it depends how strong is the gravity of the planet. It's going to be different. Does anybody know on Earth how fast it'll pick up to after falling for 1 second?
9.8 meters per second.
Yes, 9.8. Okay. Now I'm going to round that a little bit because that's extremely close to 10. More often than not, I'll do that. Okay. So some papers that are printed out, you might see 9.8 meters. You might see 9.8. Some you'll see 10. I'm going to use 10 just for this. Okay. How about after another second? Guess how fast it's picked up to? 20 meters per second. How about after another second? How fast do you think? 30 meters per second. And then 4 seconds. Do you think it would pick up to 40 meters per second? And then let's see, 5 seconds is about to crash land into the ground. How fast is it going to crash into the ground? 50 meters per second. It's been falling for 5 seconds. Okay. Let's plot this middle graph, velocity versus time. I usually approach it this way anyway. Start with the middle one and then I'll branch out from there. These graphs are going to be related to each other, but one step at a time. Scale this axis 1, 2, 3, 4, 5 seconds. 0, 1, 2, 3, 4, 5 seconds. Okay. The greatest velocity is 50, so I'll go 10, 20, 30, 40, 50. So 0, 10, 20, 30, 40, 50 meters per second. Let's plot these points, like coordinates. So like XY coordinates, but it's TV, right? So 0, 0. At 1 second, it's picked up to 10 meters per second. At 2 seconds, it's picked up to 20 meters per second. 3 seconds, it's up to 30 meters per second. 4 seconds, we're up to 40 meters per second. And 5 seconds, up to 50 meters per second. Oh, you guys do see that we're going to be ignoring air drag, right? If you considered air drag, then this graph will look a little bit different. I'll save that idea for a future date, but right now we're ignoring air drag. Everything's falling in a vacuum. Okay. Hey, does that graph look exactly like your guys' V versus T that you just made a few minutes back for the car going down the incline? It has the exact same shape, doesn't it? Ah, yeah, maybe a little bit different slope, but that's exactly what it looks like. That's a linear relationship. Is that? Now, who could tell me that you guys can get this? What is the slope of this line? What's the rise over run? It picks up 10 meters per second every 1 second. That rise over run? Okay. Isn't that called 10 meters per second squared? Right. Hey, would that be the acceleration of the ball? Okay. Suppose it's been falling for 1 second. Has it picked up 10 meters per second in that second? Yeah. Is that called 10 meters per second squared? How about if it's been falling for 2 seconds? Is it still picking up at that rate? 10 meters per second squared? How about after 3 seconds? Is it still picking up 10 meters per second at that second? No matter how long it's been falling for. Even as soon as you let it go, let's say like the first microsecond after you let it go, right? Still 10 meters per second squared, right? As long as you're on Earth, right? So we got that column. Okay. Let's do this graph down here. So we've got 0, 1, 2, 3, 4, 5 seconds ticking along. Can you guys draw this graph before I do? This graph right here. Let's see, at 1 second, it was 10 meters per second squared. At 2 seconds, it was 10 meters per second squared. At 3 seconds, it was 10 meters per second squared. Hey, you see a pattern? That is the graph, isn't it? You see it? Right, so no matter how long it's been falling for, ignoring air drag, it's always going to pick up speed at 10 meters per second per passing second. Right? Now, I told you guys that these graphs are going to be related to each other, and we've got a couple of graphs on the board, so we can already start to find some relationships. Do you guys see that the slope of V versus T is the same thing as the coordinate of A versus T? The slope of V versus T is acceleration, which exactly maps right here. And the slope is the same everywhere. See, the constant slope, constant coordinate. Like that. So the slopes of this guy is equal to the coordinates of this guy. I'm going to draw an arrow and say slope, because if you know the slope of V versus T, you can very quickly draw A versus T, because that's what it is. Like that. And there's also a relationship back the other way too. Okay. Now this one's a little trickier to think about, but I think you guys can get this. Do you guys see this rectangle right here? Okay. Does that rectangle have some area? And I wonder what the unit would be for the area of that there rectangle. The unit. Well, isn't area base times height? This has a base of some number of seconds. This has a height of some meters per second squared. What happens when you multiply meters per second squared times seconds? What unit do you get? Just plain meters per second, which describes a velocity, doesn't it? Huh. And let's get a numerical value. What is 1 second times 10 meters per second squared? What's 1 times 10? That'd be 10, and the unit would be meters per second. Ah, guess you during the first second, it goes from 0 to 10. Oh, I wonder if that'll continue. What about for the entire thing? Guys, this big old rectangle right here. Guys, what is 5 times 10? 50, and then the unit would also be meters per second. Okay, look at that. After 5 seconds, it's picked up to 50 meters per second. Do you guys think that the area under A versus T tells you the change of velocity? That's that relationship. I'm going to write area. So slopes goes this way, areas goes this way. Is that? Hey, if you look at these units, meters per second, meters per second per second, do you think that exact same relationship stores going to you just translate that right up to here to X versus T, right? I bet you could. Right? And I'm going to use that to derive an equation. I bet some of you guys know what this last graph is about to look like too. But I'm going to use that to derive an equation. Okay. So just like I took this rectangle and found the area of it, and that tells you what V versus T is. Do you guys think that the area of this here triangle tells you the displacement of the ball, like how far it's fallen off the cliff? Let's look in terms of units. Area of that triangle, is that 1/2 base height? So something to do with base times height, right? How about the units? What is meters per second times seconds? That would be meters, wouldn't it? That sure does represent a displacement. I'm gonna take this graph, I'm gonna blow it up real big, and we're gonna do some magic. Velocity, meters per second, time, and seconds. And anything that's under free fall, or your guys' graph yesterday was on an incline, just rolling down. Okay, so it's gonna be basically like that. Okay. We're gonna make this a triangle and find out what's the area under the curve, between the curve and the time axis. Okay. I'll call the base of the triangle some generic time t. So some generic time t has been ticking along, tick, tick, tick. Okay. And what about the height of this? Well, height of this is velocity, but isn't velocity? We have an equation for that, isn't it this? Okay. Oh, we're also starting from rest just for a very basic case, right? Drop, start from rest. Okay. So isn't the initial velocity 0, start from rest? So isn't the speed it picks up to acceleration times time? Okay, D equals AT. Okay. So here's what A is on this graph, right? Slope. So if I take that slope times time, that tells me the height of that triangle. That's A times T. True? Right, then the area of the triangle, which should represent displacement, like how far your car rolled, how far that ball's falling down the edge of the cliff, is 1/2 base height, because 1/2 base height for the triangle. The base is T, the height is AT. Right? Oh, that time, is that the same thing? Yeah, let's put it all together. X equals 1/2 AT squared. That's what T times T is, right? T squared. Okay. And now we have a relationship for how far something's fallen as a function of time, given a constant acceleration. Now this is only true starting from rest. But starting from rest, which is also called v initial equals 0 meters per second. Right, like that. Same thing. Okay. As long as that's true, you guys can get that, right? Now, a few minutes ago, we were saying that if you have a non-accelerating situation, you guys remember how distance was just speed times time? And then if you are accelerating, it's 1/2 AT squared. So what if you have both? What if you have starting not from rest and also you're accelerating? Can you just add those pieces together? Here's constant velocity, how far you've gone. Here's constant acceleration, how far you've gone, starting from rest. And here's the two just added together. So now if you like chuck the ball straight down, or if you gave that Hot Wheels car yesterday a push, now you have an even more generic way to put it together. You guys get it? Okay. So how far has it gone? Speed times time, or let's say velocity times time, plus 1/2 AT squared. Just add it all together. Okay. It's a graphical way to show this too, but so much time here today. Okay. So let's go back and fill in that last column and also make this graph. Okay. So let's use the simplified version just because, drop the ball or drop the car. And so, or call the top edge of the cliff point 0. Okay. And then how far is it falling from there? Well, 1/2 AT squared. So let's plug it in. Let's go 1/2 times acceleration is 10 meters per second squared, times it's been falling for 1 second, square that 1 second, and I get 5 meters. It'll fall 5 meters during the first second. Anything on Earth will fall 5 meters during 1 second. How about after 2 seconds? Scroll up, scroll over, replace 1 second with 2 seconds. Now we're up to 20 meters. Okay. Let's throw in a third second. Now we're up to 45 meters. Throw in a 4th second. Now we're up to 80 meters. And how about 5 seconds? Something's been falling for 5 seconds. 125 meters. Aren't those numbers consistent with like the ball like spacing out? Set space, right? It's getting further and further. Okay. Let's plot this real fast. 1, 2, 3, 4, 5. Go up to 125 meters. 25, 50, 75, 100, 125. 25, 50, 75, 100, 125. 1, 2, 3, 4, 5. So I plot these points 0, 0, 1, 5, 2, 20, 3, 45, 4, 80, and 5, 125. Look at that. That's a parabola graph, just like for your lab. Get that too? Okay. All right. And finally, last point today. If you do it, you guys remember system of equations from algebra? You guys remember like substitution? I'm gonna tell you guys one way to get this third equation. Here's one way to do it. Take the second equation, solve for t in terms of the other variables, substitute that into this t up here, and then do a bunch of algebra, and you can eventually get this last equation. Notice this last equation does not mention time, right? So if you're ever asked like some kinematic question and you're not given how much time has passed, or and you're also not asked for it, there's a really good chance that you can solve it with this third kinematic equation. For example, if I tell you you could throw a ball so fast, you throw it straight up in the air, and they ask for what's the maximum height. Say, well, I know it threw the ball at some speed. I know at the maximum height, the speed is 0. I know Earth's gravity is 10 meters per second squared, and I can solve for that maximum height. Right? That'd be a classic question there. Oh, yeah.
In the graphs and the.
Yeah. Yeah, so your table and your graphs, throw them in this grade tray, and then I will give you guys lab points. Right, and that is a wrap on today. Yeah, throw it in the grade tray.